Our final unit in this section is on inverse trigonometric functions. And I have a function up here. It's not a trigonometric function, but let's talk about this and see how this relates to our trig functions. So if we were to graph this function, y equals x squared, we'd get a parabola with vertex at the origin. Now if we were to try to graph the inverse of this function, we know that inverses are reflected across the line y equals x, and if we do that, we'd get something kind of like this. Now, a question for all of you, is this inverse a function? And the answer is no, this fails the vertical line test. So in order to make this first function have an inverse function, we have to just think of part of it. So what we have to do is just limit the domain. We have to say this only works when our x's are greater than or equal to 0. Okay? So we're basically cutting this parabola in half to make this work, to make it so it does have an inverse function. Now, when we talk about inverse trig functions, we have to think the same kind of way. Here's why. We know from our Algebra 2 days last year that if you graph this function, y equals the sine of x, you'll get a curve that looks something like this. Starts down here, goes up and down, etc., etc. And if we tried to come up with an inverse of this, we'd have some kind of curve that if we flip this around, we'd get something like this, this, this. It would not be a function. Okay, so we can't just talk about this entire curve. We have to somehow limit the domain, just like with y equals x squared. So what we do is we limit it between this value here and this value over here. So there is an inverse of this sine function. However, so I'm going to say y equals the inverse of the sine of x. And this is only for angle measures, so I'm going to say theta must be between negative pi over 2 and positive pi over 2. And if you like degrees, we can say that's only between 90 degrees and negative 90 degrees. Now, same thing for cosine. Cosine follows one of these similar kind of curves. It's just shifted over a little bit, so it kind of does something like this. And we're only going to look at values of cosine between these two angles. So there is an inverse, so I'm going to say y equals the inverse cosine of x. But it only works for angle measures between 0 radians and pi radians. And if you like degrees, that's between 0 degrees and 180 degrees. Now likewise, the tangent, y equals the tangent of x. If we were to graph this, we'd get a whole bunch of these curves that look something like so. And I think you'll agree with me that if we were to flip this across the line y equals x, this would fail the vertical line test. So we just look at values between these two asymptotes of the curve. So we can say, yes, there is a tangent, or excuse me, an inverse tangent function, but it only works for the values in radians between negative pi over 2 and pi over 2. Or if you like degrees, that's between negative 90 degrees and 90 degrees. Now you'll notice that I put less than or equal to signs for all of these because those values do exist. For the tangent function, the values here don't exist because our curve approaches but never touches, which is why I just used less than signs. Okay, so let's work a little more with these inverse trig functions here. So first example says evaluate the expression without a calculator. So here's what this means. It's like saying, give me the angle whose tangent is 1. So what angle would have a tangent of 1? So opposite adjacent would be 1. That angle would be 45 degrees or pi over 4 radians. Now, here's why these inverse functions here that are limited, there's only going to be one answer. We know that we could draw another triangle down here that would have opposite and adjacent the same. However, in order to be a function, there can only be one possible solution, meaning we can't count this other value as a possible solution. So only look at the values for tangent between negative 90 and positive 90, or negative pi over 2 and positive pi over 2. Okay, next one. We want to look for the angle whose sine is 0. So I know sine is opposite over hypotenuse, so I'll write that as 0 over 1. And you might look at that and say, well, that diagram's impossible because you can't have a 0 in this spot. Well, really, if we were to condense this triangle down so it's just a segment over, opposite would be 0, hypotenuse would be 1. That angle is 0 radians, or 0 degrees. Okay, last one up here. We want an angle whose cosine is 1/2. Okay, so I've got to think cosine is going to be adjacent over hypotenuse. And if we use the Pythagorean theorem, we'll find this missing side. Hey, those dimensions look familiar. That looks like it's going to be pi over 3 radians, or 60 degrees, one of those special right triangles. Now, we can think through some of these because they all deal with these special right triangles, but sometimes we don't have angle measures that work out that nicely. And in fact, you could have just typed in each of these expressions and your calculator would give you these answers, either in radians or degrees, depending on the mode your calculator is in. So let's take a look at some more examples where, hey, we don't have these nice quantities that work well with our special right triangles. So let's just type these in our calculator. So depending on the mode your calculator is in, so I'm going to put my calculator in degree mode. And if I type in this first one, the inverse sine of negative 0.7, I get this is about negative 44.4 degrees. Same thing with this second one. This one's going to be about 63.27 degrees. And this third one, this is going to be about 71.56 degrees. Now, if you have your calculator in radian, you would have found that these answers would be about negative 0.775 radians. This one here would be about 1.104 radians, and this third one would be about 1.25 radians. Realize your calculator won't give you answers in terms of pi. So for example, if you did get pi radians, it would just say 3.14, okay? Okay, so using a calculator, pretty simple here, as long as we know what to type in. Okay, let's go on to a different kind of example. Again, inverse trig functions. Use an inverse trigonometric function to write theta as a function of x. So here's what this is saying. It's saying we need to somehow just write what theta is equal to. We're not going to be able to come up with an answer because we don't have just a number here. So let's see if we can write it as an expression. So we can say, from theta we have adjacent and hypotenuse labeled. So that's going to give us the cosine. Cosine of theta equals adjacent, which is x minus 3, over hypotenuse, which is 5. Now, although we can't come up with an answer, we can think about how would we find the answer? Well, what we would do is we would take the inverse cosine of both sides. And if we do that, we end up with theta is equal to the inverse cosine of x minus 3 over 5. And that's the answer we're looking for. So it's like saying if we knew what x was, how would we find theta? Well, we'd plug it into this expression, take the inverse cosine, that would give us our answer. So when we have something like this, realize that you will not get a number answer. You won't get a measure for that angle. You'll just get an expression. Let's look at one more kind of like that. Use an inverse trig function to write theta as a function of x. So from theta, we have opposite and adjacent labeled, so we know we're going to deal with tangent. So the tangent of theta equals opposite over adjacent. Taking the inverse tangent of both sides gives us theta is equal to the inverse tangent of x plus 1 over 4, whatever that expression is. And there's our answer. It looks kind of messy, but really it's relatively simple because we don't have to do any work. We can just write this expression and be done with it. All right, let's continue. Next example, find the exact value of this expression. Now, just a few things here. It appears as if we can do this. Inverse sine and sine, they're inverse operations. They just simplify. Tangent and, oh, be careful. See this arc tangent? That's another way of writing inverse tangent. So when you see arctangent, it's the same as inverse tangent. But you would think you could just do this and come up with these answers. Now we have to be careful because that's not always the case because of those limited domains. Let me show you what I mean by this. So I'm going to make a sketch of the angle whose tangent is 2. So here's this angle, I'll call it theta. Tangent is opposite over adjacent, so there's the angle whose tangent is 2. Now I want to find the tangent of this angle. Well, it's going to be 2 over 1, so the tangent of the inverse tangent of 2 is just equal to 2. So in that case, it did work. Tangent and inverse tangent simplified. Now in the second case, it doesn't quite work because this value, this angle, is outside the domain of inverse sine. So if we were to sketch this, first of all, the sine of 7 pi over 4, well here's 1 4, 2 4, 3 4 5 6. 7 pi over 4 would be somewhere down here. So here's our angle theta. Now we know this is going to give us a 45-degree angle, so we can label some of these dimensions here. So this is going to be negative square root of 2 over 2. Here's 1, here's square root of 2 over 2. So the sine of 7 pi over 4 is going to be negative square root of 2 over 2. The inverse sine means come up with the angle that has that sine. Well, the angle needs to be limited between negative 90 degrees and positive 90, or negative pi over 4 and positive pi over 4. So the angle we're looking for is actually this angle here, which is actually the reference angle, which is going to be equal to negative pi over 4. Or for those that like degree measures, it's going to be negative 45 degrees. So we have to be careful. It appears as if we can just simplify, in this case, tangent, inverse sine and sine. However, if we're given an angle measure in this case that's outside of the possible domain of angles for inverse sine, inverse cosine, or inverse tangent, we won't simply be able to simplify those functions. Okay, let's continue. Next problem, we need to find the exact value of this expression. A little bit different kind of problem. And again, I threw one of those arcs in there. To be honest, I prefer to write this as inverse cosine, but the book uses arc cosine a lot, so I'm going to put it that way. But if I were to write this, I'd say the tangent of the inverse cosine of 2/3. So here's what this is saying. We have to start with what's in parentheses. We have to make a sketch of the angle whose cosine is 2/3. Okay, let's do that. So I'm going to draw an angle over here. The cosine, which is adjacent over hypotenuse, is 2/3. And while we're drawing this angle here, let's complete this right triangle by using the Pythagorean theorem. We get this missing side is the square root of 5. So this angle here is equivalent to this expression. We've drawn the angle whose cosine is 2/3. Now we need to find the tangent of that angle. So the tangent of that angle is opposite over adjacent, and there is your solution. So what we have to do here is first draw what's in the parentheses, then find the tangent of what we have drawn. Let's do one more just like that. So we're looking for the cosine of the inverse sine of negative 3/5. So first we need to draw the angle whose sine is negative 3/5. So opposite over hypotenuse. And you'll notice, whoops, I made a mistake here. Should have thought this out a little bit in advance. Since sine has to be negative 3/5, that quantity should be going downward. So I'm going to draw it this way. Negative 3/5. I'm going to use the Pythagorean theorem to find that missing side. So right now I have drawn the angle that's in here. So here's that angle. The angle whose sine is negative 3/5. Now I need to find the cosine of that angle. So cosine means adjacent over hypotenuse. And there's my answer. And I tell you what, drawing a sketch of this makes this problem much easier than trying to do it without. So start with a sketch. Okay, let's take a look at a couple more of these, but I'm going to make them a little bit tougher. Write an equivalent algebraic expression. Notice, here's what makes this tougher. We have this 3x in here. We have this expression. So our answer isn't going to be a number answer. Our answer is going to be some complex expression. So first, let's draw the angle that's given right here, the inverse tangent of 3x. Draw the angle whose tangent is 3x. Okay, so I'm going to put a set of axes. I'm going to make a right triangle here. And we know tangent is opposite over adjacent. So I've just drawn the angle whose tangent is 3x. Now, just like the previous two problems, we have to come up with this missing side using the Pythagorean theorem. Well, Pythagorean theorem tells me that a squared plus b squared equals c squared, which tells me that 1 squared plus 3x squared equals c squared, which I can simplify as 1 plus 9x squared equals c squared. And if I take the square root of both sides, I get 1 plus 9x squared, square root of that equals c. Careful, here's the biggest mistake people make. People start taking the square root of these parts. We can't do that. Unless you can factor what's in here, you can't take the square root of individual parts. So c, this missing side, is going to be the square root of 1 plus 9x squared. Now that we have that, that's the tough part. Now let's find the sine of that angle we have just drawn. So sine is opposite over hypotenuse. And there is your answer. Now, at this point, many students say, shouldn't we rationalize the denominator? Well, you can, but it really doesn't clean things up. You'll end up with 3x times the square root of 1 plus 9x squared all over 1 plus 9x squared, which you can't simplify at all. Don't even think about canceling the 3x and the 9x squared, not unless you can factor what's on the bottom here. So this answer is equivalent. You can write it this way, but I tell you what, when you get to calculus next year, this answer here is actually easier to work with. So realize that yes, you can write this two different ways, but you don't have to. Okay, let's try one last problem like that, then we'll be done with our notes. Last example, same kind of thing. We want to draw this angle first. So I'm going to draw a set of axes. I'm going to draw a right triangle that has a sine which is opposite over hypotenuse of 2x over 1. Pythagorean theorem tells me that a squared plus b squared equals c squared. And if I simplify a little bit, I get a squared equals 1 minus 4x squared. Or a, the missing quantity, equals the square root of 1 minus 4x squared. Do not even think about taking the square root of those individual quantities. So over here I'll write square root of 1 minus 4x squared. Okay, that's the tough part. Now I need to write the cosine of that angle we've just drawn. Well, cosine is adjacent over hypotenuse. And there's your answer. You don't really need that over 1, but since I've got it anyways, I'll just keep it there. All right, that wraps up your notes on this unit and in fact on the entire chapter. See what you can do on this assignment. When you're done here, you can start reviewing to get yourself ready for the next chapter test.